Okay, there we go. So basically, as the first part of today's tutorial, we are going to look at a case study. It will not take us very long, but essentially, this is what we're trying to understand. This was left in the last tutorial, multivariate regression, and how you can use it to control for certain confounding variables. So this is the case study that we're going to look at for that matter. There's an entire data generating or slash data loading process over here, which I'm not going to go over. Rather, we will look at the results and infer from what is given to us. So, anyway, this is the problem statement. In Southeast Asia, we often consume foods with high salt content, and high salt content is known to impact blood pressure. The National Health Survey of Pakistan estimated that hypertension affects 18% of Pakistani adults. It is well known that high blood pressure is associated with increased risk of mortality. So now we're interested in finding the causal effect of sodium intake, means salt intake, on the blood pressure of an individual. The problem is taken from a paper which is referenced over here. You may feel free to explore it on your own later if you'd like. This is where we've essentially obtained our data from. So the outcome variable is y, and the outcome variable y represents the systolic blood pressure. The systolic blood pressure normally is supposed to be around 120. Then the treatment T is the sodium intake. And essentially, the sodium intake is just a binary variable. If the sodium intake is more than 3.5 milligrams, then T is 1. It means that the person has high sodium intake. If it is less than 3.5 milligrams, then it is 0, which means that the person has a sodium intake within whatever level it is that we are allowing them to. All right, so the measured covariates, okay, so you have the treatment, sodium intake, and you have the outcome, the systolic blood pressure. And then there are covariates as well. The first covariate is age, because we think that age may be impacting both. And then the second covariate is the amount of protein in the urine of an individual, which has also been measured. We are given the data of 1 million individuals. This is a simulated example, and you already know that the average treatment effect is equal to exactly 1.05. So let's try and hold on to that number as we move on. All right, I'm going to just show you guys what the data set looks like. This is what it looks like. 1 million rows across four different columns. Blood pressure, which is the um, Y basically, the outcome, and then sodium, which is X. Sorry, it's not X, it is the treatment. And then age and protein in urea are both representing X. Basically, you can call it X1 and X2 because those are our two confounders. All right. So quickly to show you, essentially what we've done is we have split our data into two groups. One group for which the sodium intake is high, and then the other group for which the sodium intake is low. So 0, 1 वाले groups में हमने इन्हें split कर दिया. And then we look at the blood pressure means of both of these groups. For the first group that that has a sodium intake value जिसकी 0 है, which means acceptable amount of sodium intake, the average blood pressure of that group is actually higher than the group for which the sodium intake is high. So that's a bit contradictory. Our assumption was that the amount of sodium intake is going to have an adverse effect on blood pressure. So अगर किसी का salt intake high है, so their blood pressure would probably be higher. But when we look at just the means of this data set, so we realize that this is the opposite way. And when you calculate the average treatment effect using difference in means, so just like इनका आप difference निकालेंगे, that's 5.32. And we know that in actual it is supposed to be 1.05. So this is a very, very bad estimate. Anyway, the same thing has been visualized for you guys over here. And with that, moving on. Now, essentially, what we're going to try is we're going to try and estimate the average treatment effect by controlling for different variables, remembering that the true value is actually 1.05. And we're going to control for different variables using regression. So let me quickly walk you guys through what multivariate regression essentially is. इसकी हम depth में नहीं जाएंगे, but as a part of this course in Module 4, Machine Learning, you guys are going to be studying this concept as well. So, multivariate regression is going to have whatever value you are predicting on one side, suppose that is y, and then y is expressed in terms of a sequence of variables and it has an intercept. For instance, y equals mx plus c, that is a simple line. M would just be alpha in this case. Alpha is a coefficient. So you know that Y is your outcome, and then you are expressing the outcome in terms of a certain variable multiplied by the treatment plus a certain intercept. And multivariate regression is not much different. जो मैंने अभी equation बताई है, that is for simple linear regression. Multivariate regression में you are expressing one variable y, which is your outcome variable, in terms of multiple variables. So आपके पास multiple coefficients आ गए हैं, alpha 1 से लेके alpha n तक, and then alpha t is the coefficient of the treatment essentially. And you also add a constant term, which is the intercept to your regression equation. So this is an interesting model in machine learning, which is going to map different input values to a certain output value. So imagine कि आपके पास three variables हैं for prediction, and then sorry, three variables हैं as input, and then there's one variable that you're trying to predict. So essentially, you are moving in a four-dimensional space and you're trying to observe कि उन three का उस fourth वाले पे क्या impact है. Your model will basically fit your data to a certain equation, and then it will calculate how it is performing on new data. So essentially, right now, this is another example where you're trying to predict the cholesterol by using the age and exercise. So it's probably something like, for instance, you're trying to determine the impact of exercise on cholesterol, and age is a confounding variable. So जब आप इसकी multivariate regression equation बनाएंगे and you will train the model, so by assigning a certain coefficient to age, the model will control for age. Let's look at that through example now. This is the initial regression model equation that we have formed. Alpha 0 is just like I told you an intercept value वो होती है. उसके बाद alpha 1 is the parameter that you're assigning to sodium. Sodium is your treatment. And then you can ignore this last term at the end. That's just an error term that goes into your model. Essentially, equation आपकी ये start वाली ही है. So you're trying to predict y, which is the blood pressure of patients, using just sodium, which is just the treatment. So essentially अभी हम कोई भी confounder को नहीं consider कर रहे. We have age and we have the amount of protein in urea as well, but we're not considering those two right now. Okay, so let's quickly walk over what the code is doing. So essentially, X के अंदर मैंने store कर ली sodium की value, and then Y के अंदर I have loaded the blood pressure because I want to predict, essentially I want to predict Y using X, and that is blood pressure using just sodium. I've initialized my model. My model is a linear regression model. There is simple linear regression. In this case, it's simple linear regression because आपके पास सिर्फ एक variable है, एक input variable है जिसको use करके you're predicting the output. If you had multiple variables over here, for example, like this or like this, then it would be multivariate linear regression, but it would still be linear regression though. Anyway, so model.fit, that is your command. It trains your model. And then what I have done is I have extracted two different data frames. जिसमें एक data frame में I have isolated all the patients who have high sodium intake, and then in my other data frame I have isolated all the patients that have low sodium intake, and I have used my model which I trained over here to predict the blood pressures for both of those categories of patients, and then I've simply found the difference in means again. All right, this time it's with adjustment, but I found the difference in means, and it is 5.32. And if we quickly circle back over here, this was already 5.32 as well. There might be slight differences, but essentially ये इसलिए हुआ है because you didn't cater for any confounding variables to begin with. All right, and this we know is still a big overestimate of our actual value of ATE of 1.05. So now what we're trying to do is we're going to try and introduce other confounding variables into the equation as well and see कि उसका क्या impact होता है. So let's see. Now this is my regression equation. Multivariate linear regression की equation है where I have the sodium and I have the age. So basically, essentially, Y is again blood pressure, the value that I'm trying to predict. Sodium is the treatment and age is a confounder. So this is the only thing that has changed in my piece of code. And the value that I obtained for ATE now is very close to our actual value of 1.05. Now we obtain 1.0446. It means that just by controlling for age, we have almost reached the true ATE that we were trying to reach. And why exactly does this happen? Because age is a confounder. A confounder is something that affects both the treatment as well as the outcome. So age is something that may affect the sodium intake. For our data set, it does. And it's something that may affect blood pressure anyway. All right. Anyway, next, let's try and train a model using both age and the amount of protein in urea. So I'm trying to introduce another covariate as well. And the answer that we obtain now is an underestimate of our actual answer of 1.05. अब आपका answer 0.848 हो गया है. So I'm gonna give you guys a few seconds here. I'm gonna pause and give you guys a few seconds to think about why this happened. Essentially, shouldn't my value came have came closer to my actual value of 1.05? एक और कोवेरिएट इंट्रोड्यूस करने से ये वैल्यू कम कैसे हो गई?
मेरा क्वेश्चन था कि
या
जब मॉडल रन करते हैं तो क्या वो एक नया डेटा सेट निकालता है जिसका फिर बाद में मीन लेते हैं? एज सच मॉडल के मीन
नो
लेने से
नो
क्या
नो
मुराद
नो
है?
एब्सोल्युटली मॉडल ने नया डेटा सेट नहीं निकाला. मॉडल को आपने उसी डेटा सेट के ऊपर ट्रेन किया है एंड देन यू हैव यूज्ड द सेम डेटा सेट अगेन एज वेल टू सी के अब जो ट्रेन मॉडल है उसके थ्रू आप कितना एटीई कैलकुलेट कर सकते हैं.
अच्छा।
Okay, so again I'm gonna pause for a few seconds and then we'll move on from this.
शायद ये प्रोटीन यूरिया वो कोई मीडिएटिंग फैक्टर हो बीच में
So this is
जिसकी वजह
not
से
a good control. Essentially, you've basically almost gotten there anyway. अगर हम इसका causal directed acyclic graph बनाने की कोशिश करें, so we will realize that age is something that's maybe affecting both. Okay, maybe with age, like the sodium intake has increased, or with age, the blood pressure has increased anyway. But when we look at the protein in urea, so protein in urea is probably not something that is affecting the blood pressure, or it's something that's affecting the sodium intake. Probably, actually, जो sodium intake had that affects the amount of protein in urea. And similarly, the blood pressure also impacts the amount of protein in urea. It means that in a causal directed acyclic graph, this is essentially a fork. Oh, my bad. Sorry. It is a confounder. The prior one was a fork. That is what makes it a bad control. I'm not going to get into the depth of causal DAGs right now because we have that practice for our next tutorial, inshallah. But anyway, when you have a causal DAG given to you and you're trying to estimate the true treatment effect of a treatment on an outcome, you condition on or you control for a fork, but you don't control for a confounder. Are there any questions at this point?
जो वेरिएबल आप मॉडल में डालते हैं एक्स्ट्रा, उसको वो कंट्रोल कर देता है जो मॉडल है, उसको
एब्सोल्युटली,
फिक्स कर देता
एब्सोल्युटली।
है।
सो ये जो आपका मल्टीवेरिएट लीनियर रिग्रेशन का मॉडल है, हम ये यूज ही करते हैं टू कंट्रोल फॉर सर्टेन वेरिएबल्स। So this is another way for controlling, but it's still a matter of what variables should essentially be controlled for and what variables shouldn't be controlled for. अगर आप किसी ऐसे वेरिएबल को कंट्रोल कर रहे हैं जिसको आपने नहीं कंट्रोल करना, तो that will create a spurious correlation between your treatment and your outcome as well. Okay, are there any other questions before we move on? Okay, I'm gonna leave this for you guys to go over. It's the same thing. You're just referencing to the coefficients of the regression model to look at the average treatment effect. And with that, we are going to move on to our next case study, which concerns structural causal models. These were covered in, I think, lecture number 13. So let's see what we have over here. In our last session, we went over conditioning versus intervention. We're going to do some probability math as well as go over a simple algorithm to see how this works too. So suppose you have a computer program that generates a data distribution in a step-by-step manner. I have this right over here, something like this. This is called a data generating program. So we have a data generating program right now. Why do we use a data generating program at this point? Because you want to know the precise causal mechanism. You want to understand the causal relationships between different variables. And this is important in observational studies. You can change different lines of code as we looked at in our previous case study as well. Jiski basis pe you can change the data generating algorithm. You can intervene basically. And you can observe कि आपकी intervention का क्या impact है on the outcome. That's what we're going to look at again. In our last session, we went over a case study that covered Simpson's paradox. In our case study, essentially, you already had a data set, but you were trying to go from the data set towards understanding the data generating program, or you were trying to use the data set to understand or to estimate the causal impacts of different treatments on different outcomes. All right, this time we're going to do it the other way around. We're going to have our data generating algorithm in front of us. So I'm going to walk you guys through this algorithm. You have three independent Bernoulli random variables. I'm going to clarify again what a Bernoulli random variable means. It's like a coin flip. A Bernoulli variable can only have one of the two binary values. It can either be 0 or it can be 1. That's the first important thing. The second important thing is it is always 1 with a certain probability which you define. We can algorithmically calculate these as well. We can use these to map onto other variables. These are called exogenous variables or noise for that matter. The reason for that is that these are outside the scope of your model. For instance, suppose you were trying to determine the impact of smoking on cancer, and then you have another confounding variable, another a covariate which is exercise, or you have another covariate which is age. These are all the variables, the covariates, the treatment variable, and the outcome variable. All of these are a part of your model. These are determined within your model, but these variables u1, u2, u3 Bernoulli random variables are these are coin flipping variables जिनकी value 0 या 1 होगी, and these are outside your model. Like your model has nothing to do with this. In fact, इन्हें हम use करते हैं to generate values for our endogenous variables. In this case, we have three endogenous variables, which are W, X, and H. Okay, yeah, we have this is basically a mapping of the example covered in class as well. So if you guys would recall, X determines whether an individual exercises or not. W refers to whether they are overweight or not. And H refers to whether or not they have heart disease. In our problem, we are trying to determine whether being overweight leads to having heart diseases. All right. And then you have a covariate over here, which is whether individuals exercise or not, because exercising may determine whether an individual is overweight or not, and exercising has an impact on whether individuals develop heart disease or not. So you're going to assign values to X, W, and H based on your Bernoulli random variables as part of your data generating process. Using this process, we have generated 10,000 individuals for this program. So again, let me give you an overview of the generating process, which we've already covered in class. I have taken this exact example from class basically. And then we're going to look at the code that generates data according to this algorithm for us. Okay, so U1 is going to be 1 with a probability of 1 by 2. It means there's a 50% chance that U1 is going to be 0 and a 50% chance that U1 is going to be 1. U2 is going to be 1 with a probability of 1 over 3, which means that there is a 2 by third chance of U2 being 0. And U3 is exactly the same as U2 as well, basically. Anyway, so X is equal to U1. That simply means कि जो U1 की value generate होती है, which is 0 or 1, you are storing that in the value of X as well. And we know that X represents whether an individual exercises or not. So 50% chance of either. And next we have W, whether an individual is overweight or not. So W is going to be 0 if X is 1. Otherwise, if X is not 1, then W is going to be equal to U2. And we know कि इसका मतलब है if X is equal to 0, then W की probability of being 1 would be the probability of U2 being equal to 1, which is 1 by 3. And H works the same way as W, except that it uses U3 instead of U2. So very quickly, I want to show you the graph that we have as a result of this data generating algorithm as well. This is the causal directed acyclic graph that we obtained. So iske andar the variables that are left in gray are again your exogenous variables. These are not part of your model. These were just used to generate your data. And then जो आपके पास green के अंदर variables हैं along with their arrows, that is what defines your model right now. So X impacts both W and H. You may or may not add an arrow over here. This is something that we're trying to determine whether W impacts H or not. Are there any questions up until this point? Okay, moving on. So let's look at how the data generating algorithm essentially works. Basically, I still have to run from the top. So I'm going to quickly do that. And meanwhile, I will walk you through the code. So let's see. Let's just look at first these three variables that we've initialized. U1 returns np.random.binomial. This is numpy की library का ये एक function है आपके पास where you can specify n, and n is basically the value that you want to predict with a certain probability p. So essentially, this will return to me a value of 1 with the probability of 0.5. Otherwise, it will return 0. Similarly, U2 may you have 0.33, which is 1 by 3, because we know that 1 की probability 1 by 3 hai. And then for U3 as well, you have 1 by 3. Now I'm creating a data frame with these columns X, W, and H. And now I am generating 1000 rows based on, sorry, 10,000 rows based on the algorithm discussed. So first I generate X, which is just equal to U1. We know that. And then I check if X equals 1, then W equals 0, just based off of this line. Otherwise, else may I've written down that W equals U2. Similarly, if x equals 1, then h equals 0, otherwise h equals u3. And that is how I have created my data frame, which looks like this. All right, now moving on. So this is what we want to do now. Now we're given a joint distribution over the random variables x, w, and h, and we're going to try and compute different probabilities of interest. And this time, what the probabilities that we are computing are not going to be by hand. Rather, we will compute these probabilities using the generated data. After that, I'll quickly show you guys how you can do the exact same computation by hand based on your data generating algorithm again, which is just a reiteration of something covered in class. All right, anyway, so first of all, you want to calculate the probability of h being equal to 1. And we know that h denotes whether a person has heart disease or not. So for the general population, we want to determine the probability of heart diseases. All right, so let's see. If you directly compute this, you get, hold on, just let me quickly rerun this again because I think something went wrong when I ran it halfway. Okay. So the probability of H, you have simply calculated it as the mean. I'm going to give you guys a few seconds after this to think about why the mean gives us a direct mapping for the basically this value for the probability of h being equal to 1. For now, we do know that this answer is 0.1676, which is approximately 1 by 6. And we want it to be equal to approximately 1 by 6 as well, but we'll do that math later. All right, anyway, take a few seconds, think about why the mean function is directly giving me this probability. All right, would someone like to comment on this? Okay, anyway, so suppose essentially ये आपके पास एक series है which you're obtaining. So suppose this is an example of a series and I want to compute the probability of h being equal to 1. So I can simply count the number of ones which are 1, 2, 3, 4, 5, and 6. Right? And then I can take the length of h, which is 3, 6, and 9. So 6 over 9, or essentially 2 over 3, is the probability of h being equal to 1. And that's exactly how I've mapped it over here as well. So your mean works just fine for that. Because mean में आप essentially ये सारी values को sum करेंगे and then you will divide it by the number of values. When I sum them up, तो obviously it's going to give me the count of ones because zeros का sum पे कोई impact नहीं है. And then when I divide it by the number of values, that's obviously the length of h. Anyway, so now we know that the probability of people having heart diseases in the general population is roughly 1 over 6. Next, we want to find the conditional probability of h equals 1 given that w equals 1. What exactly does this translate to? I want to find the probability of people having heart diseases who are overweight. All right, so I want to see for those people who are overweight, what is the probability that they have heart disease? And I can calculate this using my data frame very easily. So first what I've done is I have isolated all the rows where W equals 1 because that's my condition, right? W equals 1. So मैंने वो rows isolate कर ली हैं जहाँ पे W 1 है and I've stored that in a separate data frame called condition data frame. I've conditioned on W. Anyway, after that, from my conditioned data frame where W was equal to 1, I have filtered out those rows where H equals to 1 as well. So ये जो H वाला data frame है हमारे पास, इसमें essentially we will have those rows where W is equal to 1 and H is equal to 1. And ये वाला जो आपके पास data frame है, conditional data frame, this contains all the rows where W is equal to 1, right? So now I can simply do this. The length of this data frame, H data frame, where W equals 1 and H equals 1, divided by the length of this one, where just W equals 1. And that gives me the conditional probability, which comes out to be approximately 35.3%, which is approximately 1 over 3. Are there any questions as far as this math is concerned? All right, moving on. So now we see that essentially the probability of heart disease in the general population was 1 over 6 approximately, and the probability of heart disease in people that are overweight is 1 over 3 roughly, which is double the probability of heart diseases in the general population. So can we immediately go to the outcome that overweight people are more likely to have heart attacks or to have heart disease? That is the question that we're trying to answer. However, using these two values, we cannot determine that because the association that we have seen between W and H right now is not causal. And let me explain to you why that is not causal. See, if you come back to your graph over here, just using the initial graph that is given to us, that was mapped from the data generating algorithm. इसमें I haven't made an arrow from W to H already because I've only mapped all of these two arrows. So I know that U1 generates X, and then I know कि since when you look at it, the third line and the fourth line, so you see कि W equals 0 when X is 1 and H equals 0 when X is 1, which automatically causes us to make these arrows. We know that X is impacting the value of W as well as the value of H. So right now, I know that the impact that I am observing from W to H is because of X right now. It is not possible to have the value of probability increased when I am conditioning on W simply because वो जो आपकी एज की वैल्यू है वो W से जनरेट हो ही नहीं रही. एज की वैल्यू is being generated using X. And you can
आप
quickly
ये
take a
लास्ट पार्ट एक
yeah.
दफा फिर एक्सप्लेन कर सकती हैं प्लीज, ये
Yes,
लास्ट वाली
of
बात?
course. Sure. First, take a few seconds and just read through this part quickly. Then we can reiterate this. All right, I think that should be about good enough. So I'm going to go over this again quickly. When we look at our data generating process, so we observe, if you just look at the data generating process for H, this last line, so H is 0 if X is 1, otherwise H is U3. So just looking at this, we know that H is determined by X and U3. W का कोई impact नहीं था in generating the value of H. That's why we didn't make an arrow from W to H, and that's why we know कि जो हम impact देख रहे हैं वो हम देख रहे हैं because of the value of X. Because the value of X was used to generate the value of W, and it was used to generate the value of X as well. It means कि essentially जो आपकी value थी X की, उसकी वजह से you observe a spurious correlation from W to H. I hope that answers your question.
जी समझ आ गई।
Okay, perfect. Let's move on then. I've just added this for your reference again to just circle back to that. And now we are going to intervene, and I'm going to clarify the difference between condition and intervention once again. Okay, so let's see. Now, so basically, first I'm going to tell you this is the probability that we have to calculate now. First, you were calculating the probability of H given that W is 1. That is called conditioning. जो आपके पास existing data था उसी में से आपने filter out कर ली वो rows where W was equal to 1, and then from those you looked at the rows where heart disease was true. Now we are going to look at the probability of H do W equals 1, which means we're going to intervene and fix the value of W to 1. Essentially उससे ये होता है. Let me just, yes. So this is what happened. All right. In brown, Cooper, you have your prior data generating algorithm. Okay, now when you are calculating the probability of H equals 1, given that do W equals 1, it means that you are intervening and you are changing your data generating process. You are actively setting the value of W to 1. So essentially इस ग्राफ के अंदर जो W की डिपेंडेंसी थी uh, X के ऊपर, sorry, X की डिपेंड, yeah, I said it right. W की dependency X के ऊपर थी, उसको आपने remove कर दिया. So you remove this arrow and you replace it with a coin flip. This is how it changes your data generating algorithm. Now W is set to 1. I have changed this row basically. That is the difference between conditioning and intervention. And beyond this point, it's very simple actually. Now, all you have to do is you have to look at the new data generating algorithm, which is written in blue, and you're going to use that algorithm to calculate the value of the probability of H equals 1 given that W equals 1. So it gets pretty simple from here onwards. So, first, let me show you in code how we have changed this
अच्छा
probability as
एक्स
well.
का एज के
Yeah.
ऊपर फिर भी इफेक्ट रहता है तो क्या वो भी प्रॉब्लमेटिक नहीं होगा कि
No,
एक्स
no.
का
No, not at all, not at all. Because essentially हमारा concern है इस arrow को खत्म करना. If X is like the exercise, तो आप exercise का impact heart disease पे खत्म नहीं कर सकते. It is still there. It is there. It doesn't really matter to us because there could be 100 other things affecting the heart disease, and it doesn't matter to us. हमारे लिए प्रॉब्लम तब क्रिएट होती है जब उसमें से कोई चीज हमारे ट्रीटमेंट को भी अफेक्ट कर रही हो. आई होप दैट आंसर्स योर क्वेश्चन.
ट्रीटमेंट को लाइक अफेक्ट करने से क्या मुराद इस कॉन्टेक्स्ट में इधर वेट है
इस
ना
कॉन्टेक्स्ट में
हमारा
आप देखें ये आपका कोवेरिएट है और ये ट्रीटमेंट को भी इफेक्ट कर रहा है. द ट्रीटमेंट इज द वेदर अ पर्सन इज ओवरवेट और नॉट. सो एक्सरसाइज इसको भी इम्पैक्ट कर रहा है इन आवर डेटा सेट और एक्सरसाइज इसको भी इम्पैक्ट कर रहा है. यू हैव टू
ठीक है
रिमूव सच पाथ्स. इसमें आपको या तो कंडीशन करना पड़ता है एक्स के ऊपर या फिर आप ये रिलेशनशिप खत्म कर देते हैं बाय इंटरवीनिंग एंड फिक्सिंग द वैल्यू ऑफ डब्ल्यू. अगर मैं डब्ल्यू की वैल्यू को जीरो पे फिक्स कर दूं तो इट्स नो लॉन्गर डिपेंडेंट ऑन एज. बाय फिक्सिंग द वैल्यू ऑफ डब्ल्यू टू जीरो I can essentially compute the average treatment effect of W on H, or rather I can see के क्या probability है of a person developing heart disease given that they are not overweight. और जब मैं W को 1 पे fix करूँ तो I can look at the probability of a person developing heart disease given that they are overweight. So essentially by intervening and fixing the value of W मैं ये dependency खत्म कर देती हूँ. Is that
अच्छा
all
तो
right?
जब आप फिक्स कर लेती हैं डब्ल्यू को तो एक्सरसाइज कर रहा है या नहीं कर रहा फर्क नहीं पड़ता वो ओवरवेट होगा ही होगा क्योंकि हमने वैल्यू फिक्स कर दी है
Absolutely, exactly. एंड दैट एक्चुअली डिपेंड्स कि आपने इंटरवीन करके वैल्यू को फिक्स किस पे किया है. अगर मैं वैल्यू को 1 पे फिक्स करूं तो आई नो दैट अ पर्सन इज ओवरवेट. इफ आई फिक्स इट टू 0 आई नो दैट अ पर्सन इज नॉट ओवरवेट. वी आर गोना ट्राई एंड डू बोथ ऑफ दोज एक्चुअली. Okay, with that moving on. So now I want to change my algorithm to match this new data generating process. And इसको change करना बहुत easy है. U1, U2, U3 नहीं change हुए. They are exactly the way that they were. X is still the way that it was, X equals U1. And H is still the way that it was as well. If X is 1, then H is 0. Otherwise, H equals U3. And this is what I've changed. Now W is equal to 1. I have intervened and I have fixed the value of W to 1. And I have generated another data frame now. अब उस data frame में when I look at the different probabilities, then the probability of X being equal to 1 is 0.49. The probability of H being 1 is, which we already computed once as well, approximately 1 by 6. But the probability of W being 1 is equal to 1 because W अब है ही 1. This is what the do operator does for you. एंड विद दैट लेट्स मूव ऑन. जब आपने अपना डेटा जनरेटिंग एल्गोरिथम चेंज कर लिया और W की वैल्यू को फिक्स कर दिया बाय इंटरवेंशन, नाउ यू कैन जस्ट कंप्यूट दिस थिंग, probability of H equals 1 given that W equals 1, and this process remains exactly the same as it was before. Now the result that I obtain is 0.1603, which is again approximately 1 over 6. So this is how you have intervened and found the probability of H equals 1 again. Similarly, I can intervene over here, set this value to 0, and then see how that impacts the probability that I will find. So let's give it a few seconds. Hopefully it should run fast. Okay, for the sake of saving time, I'm quickly gonna run it again. Essentially, while this code runs, we can make an important observation though. The initial probability of heart disease in the general population was 1 over 6. Now, when I have intervened and fixed the value of W to 1, like now I'm saying कि आपने overweight people की देखनी है सिर्फ. So in that case as well, the probability of heart disease is approximately 1 over 6. What does that tell us? That tells us कि overweight होने का कोई impact नहीं है on heart disease based on this data. So now, of course, I have to change this to 0 as well. Oh, my bad. Because मैंने W को 0 पे fix किया था, and this is also approximately 1 over 6. And when I fixed this to 1, that was also approximately 1 over 6. So essentially, that tells me that there is no impact of being overweight on the probability of developing heart disease. When you use this to find the average treatment effect, let me just show you over here as well. This is what we did last time. So हमने ये दोनों probabilities calculate की. They both were approximately 1 over 6. And when you use these probabilities to find the estimated average treatment effect, it is 0, which tells us that there is no relationship between those two. Or let me clarify, it tells us that there is no causal relationship between those two, because जब हमने intervene नहीं किया था, तो हमने ये observe किया था कि there is a 30 कि like 33% people did have heart disease that were overweight. That was the difference. But when we intervened, we observed that that was just an association. When we intervened to observe whether the association is causal or not, we realized that the association is not causal. And again, reiterating that it makes complete sense because in our data generating algorithm, now I'm not talking about real life. Real life में होगा impact, I'm sure. But for our model, जिसके through हमने data generate किया, H was never determined by W. All right, so I'm gonna pause over here for a few seconds and let you guys think about one particular scenario. First, we'll go through this. One of the most important takeaways right now should be that probability of H given that W is equal to 1 is generally not equal to the probability of H given that do W equals 1. But there is a case where these are equal as well. So I want you to take a few seconds and think about that case. ऐसा कौन सा केस है जिसमें ये equal हो भी सकती हैं? Okay, so essentially, this has helped us establish ke, or rather, this is not what I was talking about. These are not generally equal. This thing is sometimes, right now, we observed that it was equal to the probability of H for the general population as well. So essentially, what happens is that if W actually has a causal effect on H, if there is a causal relationship between these two, then those probabilities may be equal as well. On that note, are there any questions before we move on to our next probability math practice question?
अगर कॉजल रिलेशनशिप है भी, लेकिन अगर कंफाउंडिंग फैक्टर्स हैं, तो तब तो 80 ये वो वाली प्रोबेबिलिटी और डू वाली प्रोबेबिलिटी तब भी फर्क नहीं होगी।
Could you come again?
आपने अभी ये कहा था कि गिवन वाली प्रोबेबिलिटी और डू वाली
Oh,
प्रोबेबिलिटी
no, no. I
प्रोबेबिलिटी तब।
absolutely mistakenly started with the wrong question. What I meant to say was कि हमने जो दो probabilities अभी equal observe की थी, this is generally not equal. जो दो probabilities हमने equal observe की थी, which was the probability of heart disease in the general population and the probability of heart disease given that do W equals 1. Those two were equal in our case, but those two are not always equal. So my question was कि when are those two not equal to each other? And वो तब होता है जब कोई causal relationship exist करता हो. So आपको directly अगर ये values दी हुई है and they are equal to each other, तो you can instantly say that there is no causal relationship between these two variables. I hope that makes sense.
ठीक है।
Okay, I'm gonna
आगे सम।
reshare my screen and we're gonna move on to, well, I seem to have lost the OneNote tab. Okay, just give me a few seconds. There we go. So just to reiterate very quickly, I would like to go over this problem as well with regards to probability. And then I have another example too. So, first of all, you were required to calculate. I'm not going to find the probability of heart disease in the general population. Or rather, let's do that actually, because we can build off of it. So, suppose you have to find the probability that H equals 1. So, let's see. If H equals 1, it means that X has to be 0. That is the first thing I can decide. Because if X was equal to 1, then H could never be 1. Then H would have definitely been 0. So, this means that the probability of X equals 0, and there is one more thing as well. So suppose अब हमने देखना है कि H 1 है या नहीं है, and if H is 1 it means that X is certainly 0, and then if X is 0 then H is equal to U3, right? So U3 must be equal to 1 as well in order for H to be 1. So this is what I'm trying to find. All right, so probability of X equals 0 and U3 equals 1. Hold on, just give me a few seconds. Okay, anyway, so let's see. The probability of X being equal to 0, X depends on U1 basically. So this means that U1 equals 0, because if U1 is 0, then X will be equal to 0. And then I can multiply this with the probability that U3 equals 1. Now वन की आपने probability देखनी है for zero, and we know that there's a 50% chance it's one. So of course there's a 50% chance that it is zero as well. For U3, the chances of it being one are 1 by 3. And that is how you obtain 1 over 6. All right, which is exactly the value that we found. Well, not exactly, but like जो हमने पीछे value find की थी in our notebook, using the data that we had generated using our data generating algorithm, it was very close to 1 over 6 as well. So now I'm showing you how you can obtain the same thing using your probability math just by looking at the data generating algorithm as well. Because in an exam, if you were given a data generating algorithm, you are not going to be able to run it, obviously. So you should be able to do this directly as well. So now suppose you have to find the probability that H equals 1 given that W is 1. This is the next value that we found importantly. So let's see what we can do over here. Now your data generating algorithm has been changed. This is what you have over here. All right, so
ये तब नहीं होगा
essentially,
अगर आप 2 की प्रोबेबिलिटी कैलकुलेट कर रही होती।
oh, yeah, yeah, you're absolutely right. I skipped ahead. You are right. Let's hold on to this for our next question. Absolutely right. So अभी हम W की value को fix नहीं कर रहे by intervention, rather we're just observing from our given algorithm. So if W is equal to 1, that means that X cannot be equal to 1, right? इसका मतलब है कि X must be equal to 0. That's the first important thing for W to be equal to 1. The second important thing is that U2 must be equal to 1. So this is what we have been able to find. So I'm just going to write this down over here. According to our conditional probability equation, this basically means probability of H equals 1 and W equals 1 divided by the probability of W equals 1. We essentially do not need to go all the way here, but I have found that students sometimes struggle with this as well. So just to reiterate how this works. So let's see. Now H equals 1 and W equals 1 को आपने देखना है. So for H equals 1 we have, so for H equals 1 essentially you have to ensure that X must be equal to 0 and U3 must be equal to, well, U3 must be equal to 1. So I'm gonna write this down over here. Into the probability of U3 equals 1 into the probability of X equals 0 into the probability of U2 equals 1. Let's see where I'm going with this. So Nietzsche, you have the probability of W being equal to 1. And we know that in order for W to be equal to 1, again, X has to be equal to 0. And we know that U2 has to be equal to 1. Count my bad. So essentially, there are some things over here that I can cancel out. You can cancel out this, and then you can cancel out this and this. So essentially, this is what you are left with. Now, the probability of, I'm just going to get rid of this real quick. Oh, my bad. We absolutely, I think, do not write this thing down twice. And that is how that cancels out. So you're only left with the probability of u3 being equal to 1. And we know that u3 is equal to 1 with a probability of 1 over 3. And approximately 33.3% is the answer that we obtained for that data generating algorithm as well. So with that, I'm going to add our final important example as well. Let's see. Now we're going to intervene, and now I'm going to set the value of W to 1, essentially changing my data generating algorithm. So you have to find the probability that H equals 1, given that do W equals 1. And let's see. So now the thing is कि आपने W को 1 पे set कर दिया. But if you look at the data generating process for H, it doesn't depend on W at all. H depends on X and it depends on U3. And we know कि U3 तो किसी भी चीज पे depend नहीं करता because it's a Bernoulli random variable. What does X depend on? X depends on U1. If X depends on U1, U3 doesn't depend on anything else. It means कि H की dependence right now it's only on U1 and on U3. H has no dependence on W whatsoever. So this intervention shouldn't make a difference for us. All right, anyway, so let's try and calculate it. In order for H to be equal to 1, again, we know that X must be equal to 1, and I'm actually not going to write down this entire process again. We know that U1 must be equal to 1, and then we know that U3 must be equal to 1. So essentially 1 over 2 into 1 over 3, the exact same math that we did before. It gives us 1 over 6. Something would have changed in our algorithm अगर इसकी value को fix करने से either x पे कोई impact होता या h पे कोई impact होता, which essentially just means कि हमने देखना है h पे directly या indirectly कोई impact हुआ है या नहीं. So, in conclusion, fixing the value of W made no difference to H whatsoever. I could have fixed this to 0 and it still would have given me the exact same answer. Are there any questions at this point?
जो सेकंड वाली इक्वेशन है उसमें एच इज इक्वल टू वन और डब्ल्यू इज इक्वल टू वन की प्रोबेबिलिटी निकालने के लिए आपने बस इंडिविजुअली एच इज इक्वल टू वन और डब्ल्यू इज इक्वल टू वन की प्रोबेबिलिटीज को आपस से मल्टीप्लाई कर दी है.
नहीं नहीं essentially आपने देखा है the probability of H equals 1 and W equals 1. So जब मैंने इन्हें individually लिखा तो I realized कि W के 1 होने के लिए X has to be 0 and U3 has to be 1, correct?
जी.
And in order for H to be equal to 1, um, nahi, hold on. This was for H, right? For in order for W to be equal to 1, आपने
एक्स को भी जीरो होना है.
yeah. So in order for W to be equal to 1, you have to ensure that X is 0 and that U2 is equal to 1. So अब आप ये देखें ये जो मैंने चीजें लिखी हैं इसमें x equals to 0 common है. That's why I wrote it
अच्छा.
down only once.
ठीक है.
Okay,
ठीक है.
because ये and है, so you have to see the probability that H equals to 1 and W equals to 1.
ठीक है.
So उसको हम simple Bernoulli variables में जब express करें तो इसके ऊपर फिर repetition आ जाती है. अब इसको मैं अगर further expand करूं तो x के 1 होने की probability just meant U1 के 0 होने की probability. I hope that
ठीक
makes
है.
sense.
आगे समझ.
Okay, are there any other questions at this point? Okay, so in order to help you guys out with practice, I will attach another probability ka sawal for a data generating algorithm against its solutions, and I would highly recommend that everyone tries to attempt it on their own. And I think one should be available in your homework as well, and then you should be good to go. That will be all for today. Thank you.